presentation. Thanks to the organizers for the wonderful conference. I will talk mostly about this paper that I wrote with Damon Binder, Shai Chester, and Yifan Wang, although I'll also mention other related things. So, starting more broadly, there are two goals of the type of stuff that I'm going to be talking about, the SCFT. And one would be to use the bulk to compute CFT or QFT quantities. And the other one would be to use the CFT to learn about bulk. And so an example of how we can use the CFT to learn about bulk would be, for instance, to obtain the flat space S matrix for scattering of gravitons in string theory or M theory from CFT correlation functions in cases in which we can compute those CFT correlation functions. In this talk, it will be mostly learning about the CFT quantities, but there are other instances of similar things to what I'll talk about where one can, the goal would be to learn about the bulk. Okay? So the case that I'm going to be talking about is the duality between SUN and equal 4 superannuals with tilde coupling GML squared n. So that's on one side, and on the other side, this is dual to type 2b string theory on AES5 sub S5. Okay. And when n and lambda are large, then this is described by supergravity. On this side, 1 over n corrections would correspond to loops in the bulk. And 1 over lambda corrections would correspond to high derivative corrections. So supergravity is a two-derivative theory, and we have high derivative corrections. So what do I mean by high derivative corrections? Well, the 10D action, effective action, would look like this. So the first term would be the integral of the Einstein-Hilbert term plus its supersymmetric completion, and then the next direction is some fourth power of the Riemann tensor. So I'll just write this as r to the 4th. The next term would be d to the 4, r to the 4, and so on, plus the supersymmetric completion. And it's kind of an embarrassing thing, but this is the, the r to the Riemann to the 4 is the first correction to supergravity, but it's not, this term is not, and its supersymmetric completion is not completely known. So I think that's probably one of the remarkable things that I'm going to be talking about is that I'm going to be computing Witten diagrams with interaction vertices that come from this r to the 4 and d to the 4, r to the 4. And even though the full supersymmetric completion of these terms is not known, the way that contribute to CFT correlation functions in n equal 4 superannuals would be determined. Okay? So, so the topic of this talk would be one of the lambda corrections. I'm not going to be talking much about the 1 over n corrections. So what does a CFT correlator look like? So let's just do 4-point functions. So whatever operator we want to look at, there's a disconnected piece, which I'll normalize so that it doesn't scale with n or lambda. And then there's an order 1 over n squared term that comes from tree level Witten diagrams. And this tree level term, this is tree level Witten diagrams, is going to have a 1 over lambda expansion. Of course, all of these are functions of the coordinates of the points, whose correlation function for the operators correlation function we're computing. But here I'm just showing how the dependence, what the dependence on n and lambda is. So the first term doesn't scale with lambda, lambda to the 0. The next term looks like 1 over lambda to the 3/2. The next term is 1 over lambda to the 5/2, and so on. So this one comes from Witten diagrams with supergravity vertices. This comes from Witten diagrams with R to the contact Witten diagram with R to the 4 vertex. This is a contact Witten diagram with E to the 4, R to the 4 vertex, and so on. And this scaling is due to the fact that in the ADS-CFT correspondence, I didn't write this relation here, so I'm probably going to get it wrong. So lambda to the yeah. Okay. So in other words, if we have L over L string, this goes like lambda to the 1/4. And the point is that this term over here has 6 more derivatives compared to that term. So it's going to be suppressed, its contribution is going to be suppressed by a power of 1 over radius of ADS to the 6th power, and 1 radius of ADS to the 6th power is lambda to the 3/2. So that's the reason for these scalars. And this has 10 more derivatives, so this has 6 more compared to that. This has 10 more compared to that. So it's going to go like 1 over lambda to the 5/2.
Okay, good.
So in this talk, we're going to do this one, and that one. So up to a 1 over lambda to the 5/2. And of course, this will have order 1 over n to the 4th.
So why aren't there d squared r to the 4th?
They're not allowed by the
Okay. Is there some canonical choice of the metric here? Because by field redefinition, you can change a lot of the structure, I think. So that's the usual story with the, when the S matrix is computed, you have to do something to get the action.
So the variant statement is that at the level of scattering amplitudes, these are the vertices.
Well, from the scattering amplitudes, you can only read off the metric up to field redefinition.
Correct.
So, and if I do field redefinition on R, then it spits out.
So this picture with the effective action is sort of heuristic because the field redefinitions involved. The invariant quantity is the S matrix.
Yes.
So you can take everything that I said and rephrase it in the language of the S matrix. And then the point is that there's supergravity scattering, and then the next direction would come with L string. It would be suppressed by L string to the 6th power, which is what I'll do because I mean, given that these things are not completely known, I can't possibly use them. So, okay. So, I guess I can keep using this board. Probably more visible. Okay, so what correlation function is what I'm talking about? It's covered in yes, it's not reviewing anyway. Of some half BPS, I'll be talking about 4-point functions of half BPS operators in N equal 4 super MLs. What half BPS operators are these? I got it. Good. What half BPS operators are these? Well, N equal 4 super MLs has field content, has the gauge field, has some scalars, which I'll apply I, and fermions. So there are 6 of these. They transform in the 6-dimensional representation of the SU4 R symmetry. And the operators for 4-point functions I'm going to be looking at, I'm going to call them SP, and their semantic form is trace applied to the P. I'm not writing down the I indices, but they're symmetrized and the traces are removed. So these are operators of dimension P, and they transform in the representation of 0, 0 of SU4, the SU4 R symmetry. The lowest dimension 1 is the one with P equal 2, and that transforms into the 20 prime representation of SU4. Okay, so 4-point functions of these. I'm not going to be doing all 4-point functions. That seems to be hard. Well, the hybrid corrections. I wouldn't know what to write on. So I'm going to be looking at the 4-point function of 2 S2s and 2 SPs for arbitrary key. So what does this 4-point function look like? It's 1 over, well, it's got some free theory part plus 1 over x12 to the 4th, x34 to the 2p, or xij is x minus xj, times 6 functions of u and v. Or u. So I'm going to denote these conformal cross ratios by capital U and capital V. So x12 squared, x34 squared, x13 squared, x24 squared. And v is the same thing, but with all 1 integer with 3. Okay. So these different 6 functions of u and v correspond to the different ways of contracting the SO6 indices, and they're just 6 ways. So I will compute for you this 4-point function at this order 1 over n squared up to 1 over lambda to the 5 halves. So to compute it, what am I going to use? This 3 things. Word identities, supersymmetric word identities. Now in space. Flat space limit. And supersymmetric localization. Because the novelty of this work really is the use of supersymmetric localization in this computation, so that's what I'm going to be focusing on mostly, but I want to say a few words about the first two first. So the first one, the word identities, imply algebraic relations between the 6 functions of U and V. This is a particular thing that happens in n=4 supersymmetry and 4D. It doesn't happen in other dimensions. There are relations, but the relations are not algebraic. That means that this correlation function over here can be written as some 3-part plus 1 over x1 to the 4, x3, 4 to the 2p. That's some prefactor that depends, that carries all the SO6 R indices. And then there's a single function that I'll call P of U and V. I think I missed the code H if I remember correct. Depends on. So the goal would be to determine this function, T of U and V. And this is going to have the same type of expansion as the 4 did. Okay, good. So that's why this is
just for, I think it's not what I need. I need to confirm. It's not H.
I think it's H minus the sharp part. It's
Close.
G. What that was.
What do you call G? Okay. Thank you.
But it's very similar.
All right. This is, I'll call it T.
Just to.
Okay. So, okay, good. Okay. So the second thing was the now amplitude. So we can either write down this function T of U and V, or we can do a Mellon transform. When you write it down, yes, T squares. So it looks like this. So there's U to the S over 2, V to the little U over 2 minus V plus 1. And there's some yellow functions. 2 minus S over 2, gamma of V minus S over 2. And there's 4 more gamma functions that depend on T and little u. And then there's the Mellon amplitude that's a function of S and T. And here little u is 2p minus S minus by definition. So instead of having a function of u and v, we can have a function of S and T. And we can go between the function of S and T to the function of u and v and the other way around using formulas like this.
So U for you is 1 for channel.
Sorry?
U is 1 for P1 plus P2 squared.
P1, yeah, I'm trying to use the Peskin and Schroeder conventions for scattering amplitudes for the Mandelstam invariance. So, yes.
So it will pose the question, what is S plus T plus U?
Yeah, well, I'm going to relate these to scattering amplitudes. U is going to be P1 plus P4 squared, and T is going to be P1 plus P3 squared, and S is going to be P1 plus P4. So the properties, the reason why this is good is because it has the following properties that allow us to determine M up to a few constants. So the properties are the following. First one is crossing symmetry. It follows from the crossing symmetry of the 4-point function. And this implies that M of S and T is the same as M of S and U. for general P. So the 4-point function is S2, S2, SP, SP, so we can interchange the two S2s or the two SPs, and this is what that implies. But for P equal 2, when we have S2, 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 there are more crossing relations, and that also implies that, so just for P equal 2, M of S and T is the same as M of T and S. Okay? So that's one property. Second property is that at large S and T, this M of S and T is related to the scattering amplitude of gravitons, closed string states in type 2D supergravity. So in 10D flat space, so we can scatter gravitons and their superpartners, and the scattering amplitude looks like this. There's some overall factor, depends on the polarization of these gravitons or of whatever particles we have. In 10 dimensions we have kinos, kilotons. So there's a polarization dependent factor. But it's all multiplied by a single function of S and T, where now S and T are the Mandelstam invariants in NG. So supersymmetry, because of supersymmetry, this is true. The scattering amplitude in 10D takes this form.
And where's the P dependence? You said M sub P is related to.
Well, in 10D it's flat space, there's no P dependence.
No.
Yeah.
Well,
There is
yeah,
an
different
overall
function.
factor that depends on P, but it factorizes.
P is going to go away in the
P.
relation.
Oh,
So all the MPs are going to be related to the same object in 10D.
I see.
It can be magic.
Does it go away, but it factorizes into something relatively trivial?
Well, you can understand that overall P factor, so what I'm saying is probably, if you define it appropriately, it goes away.
So that's the angular momentum S by the...
Yeah, that's right. So the relation between, okay, so I can just tell you the relation. So the relation is that F of S and T. So this is flat space. So there's a normalization factor times the limit the radius of ADS goes to infinity. Oh, you can write a relation many ways, but alpha minus 4 minus P and P L squared over 2 alpha S, L squared over 2 alpha T. There's something equal relation like this. Because in this relation, we're taking L to infinity. It's only, so here S and T are the Mandelstam variables in 10D. And the arguments of MP are not the Mandelstam variables. They are these functions that we're integrating over in the Mandelstam transform. So in order to get f of S and T, we have to evaluate M sub P at L squared to S over 2 alpha and L squared T over 2 alpha, and then take the limit when L goes to infinity. So it's just the leading term at large S and T in M sub P that would contribute to this limit. So this is a constraint on what this Mellon amplitude is. The constraint being that at large arguments it has to be consistent through this formula with a flat space scattering amplitude. So here the limit, the way I wrote this formula, the limit is taken, so you just write down the CFT correlator, write down one, figure out what M is, and then write it in terms of N and lambda, and then convert these quantities through the ADS CFT dictionary to L string and G string, and the radius of ADS. So this is taken as fixed LS. So GS, G string is G and L squared over 4 pi. And as I wrote before, L over LS lambda 1/4. You just convert all these CFT quantities into G string and L string and the radius of ADS, and then take this limit, and then you're supposed to get the flat space scattering amplitude. Okay. So the good thing about it, the reason why this is useful is that we know what this function, we know something about this function of S and T. In particular, well, okay, let me write it down. So maybe I want to leave this definition here. So f of S and T I didn't write the overall normalization, so the overall normalization is not going to be important. 1 over SU. And then there's zeta of 3 over 32, L string to the 6, and then zeta of 5 over 2 to the 10, S squared plus E squared plus E squared, S to the 10, and so on. And then it has higher order terms in G string. So this is the G string to the 0 piece, and then the correction within G string. This formula is known completely at leading order in G string. It's in Polchinski, it's some ratio of gamma functions. The analog of the source of Shapiro amplitudes were have to be used here. Okay. So this comes from the gravity term. This comes from R to the 4. This comes from B to the 4, R to the 4, and then so on. So this is what I'm going to have to match onto the terms that I wrote down in the expansion of MP that are multiplied by lambda to the 0, 1 over lambda to the 3 halves, 1 over lambda to the 5 halves.
So all of these are determined by supersymmetry?
This? These are not determined, the coefficients are not determined by supersymmetry. I mean, this is done from a Gaussian calculation.
I see. So the part which is determined by supersymmetry is whether it's 0 or not?
Well, also the powers that appear. So, for instance, there's no LS to the 8.
Or other powers of SFT?
Yeah, the powers are SMT. Well, for the first few terms, afterwards. So the first few terms are F terms, and then there would be D terms, and the D terms are not constrained, the F terms are constrained, and only the first few are F terms.
So LS to the 8 is just going to be what S plus T plus U, which is constant.
Sure. We can do, well, okay. Yes, that's true. Not the reason why that one is gone. If I were to write the same thing in 11 dimensions, then the first few terms would be this one, the best explanation is commercially calculated.
It's also scattering amplitude for scalars, basically, that you wrote down, because principally we're supposed to do gravitons.
Well, okay, good. So this is the scattering amplitude for all superpartners of the graviton at 11 dimensions. What I'm going to be looking at is gravitons so that I relate it to a four-point function of scalar operators in 4D. So I'm going to take the gravitons to be polarized, to have their momenta within a 5-dimensional subspace and be polarized in the transverse directions.
So just to complete the discussion, so supersymmetry in particular fixes all this polarization dependent refactor.
Yeah,
Not of all this.
that's right. Supersymmetry comes in. Yeah, okay, good. Thank you. Supersymmetry comes in here, where it's just one function. Otherwise, it would be many functions.
Also, so I'm a little confused. So you factor out the 3-bit,
Yeah.
and then you take the function that you call P.
Yeah.
Is that, I would expect T to be sort of the sum of all connected written diagrams.
It's not the free, it's the disconnected piece.
But you wrote 3
Oh, did I write the free? I meant disconnected, yes.
I'm sorry, right. Okay.
So it should be free, right?
Free, is it free field theory or free?
Free field theory. That's like
But then you also get monoprice correct correction.
Can you
That's-
either of them is okay.
Okay, these things are not going to affect the 1 over lambda to the 3 halves, 1 over lambda to the 5 halves. It's just going to affect what I call this lambda to the 0. So lambda to the 3 halves and lambda to the 5 halves, this distinction is not important, whether it's free or it's disconnected. Okay. So the other property, the lambda property,
And one more question, so for the origin computation, involves 11 only?
yeah, 2 is 0. Well, the expression that I wrote down that I just directed. I think it's, no, not for, sorry. Well, the next few terms are in the GS expansion are also known, but not required for that.
At the genus 1, you can basically write as many as you want. And already in genus 2 is a thing.
And the third property of the memory amplitudes that's going to determine them is the pole structure. So exchange for well understood for tree-level Witten diagrams. Exchange diagrams have poles, and it's understood where the poles are, and contact diagrams. For contact diagrams, MP is a polynomial in SMT. I guess that's one really useful thing about this formula is that it makes contact Witten diagrams very simple. If the contact Witten diagram, if the interaction vertex doesn't have any derivatives, then this is just a constant. If it has derivatives, then this is just going to be a polynomial in SMT of degree number of derivatives in the vertex divided by 2. So then I can write down for you, I can make a table of what this MP would be. By the way, exchange Witten diagrams will have only for supergravity vertices. For these higher derivative terms, they're purely contact diagrams. There are no identical. So we have the same P. So this will just be an order 1 over n squared, and this is the expansion in 1 over lambda, and it's a function of S and T. So the first term would be 1 over S minus 2, T minus P, U minus P. This comes from supergravity. And this would have, well, in principle, it could look like this. We have an expansion in 1 over lambda, 1 over lambda to the 3 halves, 1 over lambda to the 5 halves, and so on. And that would be a constant. We start only with 1 over lambda to the 3 halves. Be a term that looks like S. S squared. S squared plus B squared plus C squared. Oh, sorry, S squared would start with 1 over lambda to the 5 halves. And so on. So I'm trying to write down these 1 over lambda expansion in a different way in terms of some nice basis of functions. Okay. This one, this term and this term won't be there. The supergravity only contributes to order lambda to the 0. Oh, I'm sorry. This thing isn't. Okay, no, I got it. Sorry. So, in the flat space limit, this expression must reduce to the formula for the scattering amplitude. So this term over here becomes 1 over STU. That's the behavior of the supergravity piece in little f that I erased. This thing goes like a constant, so maybe I can, so f of S and T was 1 over STU plus something with zeta of 3 plus something with zeta of 5 multiplying S squared plus B squared plus C squared, and then so on. So this was the GR piece. So this term here, this whatever this coefficient is, will be related to this coefficient using this the flat space limit formula. This term here will be related to this coefficient, to the zeta of 3. And these two will be related to the zeta of 5. In particular, the coefficient of this S squared is going to be 0. That's from the flat space limit formula.
It's the prefactor there is S and the second term.
SSS.
So how can you fit it with the absence of the results?
Well, so from the flat space limit, there's no term over here that goes like S. So the coefficient of that any term would be 0. This would be a power in between 3 halves and 5 halves.
But I think a point is that for P different from 2, this doesn't have to be symmetric in S, T, and U, but only under T and U. So S by itself.
S by itself would be, so these terms are allowed only for P not equal to 2. For P equal to 2, there's extra crossing relations that kill S and S squared. Because then you'd have to have S plus T plus U, and here you have to have S squared plus T squared plus U squared. So let me write down what happens for P equal 2. So for P equal 2, this is in general, for P equal 2, this line isn't here and this line isn't here. So then the claim is that in order to determine what this function MP is, up to order 1 over lambda to the 5/2, we just have to count the number of parameters that we need to determine. So if we want to determine it up to order lambda to the 0, we have to calculate. So suppose we don't want to use the information from the flat space. If we want to calculate it up to order lambda to the 0, we just have to calculate one number from the CFT. If we want to know it up to order 1 over lambda to the 3/2, we also have to calculate just one number from the CFT. If we want to calculate it up to order 1 over lambda to the 5/2, we should calculate 4 numbers from the CFT. When p is not equal to 2. When p is equal to 2, it's simpler because these two are not here. So there'd be one number, and here would be 2 numbers that we have to calculate from the CFT. So these are just pure numbers that one would need to calculate. So let me write it down so that it's clear. So when p is bigger than 2, we need, in order to determine the amplitude, we need to determine 1 plus 1 plus 4 numbers, and then so on. We can keep going if we wanted. The flat space limit gives, so from the flat space limit, if we wanted to use the flat space limit, we'd be able to determine one number, and 2 numbers, the largest power. In order to know the amplitude completely, we need 2 extra numbers over there. And when p is equal to 2, we need, so these 2 are not there, so we need 1 plus 1 plus 2. And the flat space limit gives 1 plus 1 plus 1. So in order to determine the Canal amplitude of the corporate function of order 1 over lambda to the 5/2, we need to compute one extra number at the order of 1 over lambda to the 5/2.
Sorry, again, maybe you said maybe it's
Yeah.
if you know, you mentioned you know all the numbers in the table of imports. How do you know that your terms in SE or S function? So you know all the properties of it and PST that has between these numbers.
So if you know all the numbers in there,
know the table you brought briefly.
if you know all these numbers, you know the amplitude up to order 1 over lambda to the 5/2, because the next terms in higher powers will start contributing only later. So up to this order, these are all the ones that can contribute, because up to this order, the largest power of STU must be quadratic, because that's what has to match the flat space limit. So up to order 1 over lambda to the 5/2, the metal amplitude cannot grow faster than quadratic in STU.
Okay.
So for the rest of the talk, here's a preview. I'll show you the supersymmetric localization computation that gives a function of lambda. So in particular, at every order in 1 over lambda, there's going to be one extra number that I will be able to compute. So what does it mean? What I mean is that at this order, or that order, so order lambda to the 0, or 1 over lambda to the 3/2, there's going to be several ways of computing the same thing. One way would be using the flat space. So there's, for instance, at 1 over lambda to the 3/2, there's just one number that we need. We can compute one number from the flat space limit, but we can also compute one number using supersymmetric localization. So in that case, that would be a precision test of SCFT beyond supergravity. You can compute something from the field theory and also compute it from the gravity side. So this would be an SCFT check at order 1 and 1 of lambda to the 3/10. And I think the one of the order 1 of lambda to the 3/10 is actually pretty cool that we can actually check the SCFT beyond the supergravity approximation, even though we don't know the full action. We don't know all the A derivative terms of the reaction. And for t equal 2, using Flassby's limit and supergravity, and so we'll be able to determine the correlation function completely up to order 1 over lambda to the 5/10. So we'll know the four-point function up to 1 over lambda to the 5/10. And for t bigger than 2, we need some extra input to determine the correlator up to 1 over lambda to the 5/10. But thankfully, that extra input is provided by Fernando and Jesse and Eric Perlmutter from consistencies of these tree-level amplitude with genus 1 amplitudes. Okay. Good so far? So let me now go to the supersymmetric localization aspect. So the idea then for the rest of the talk would be to compute one function of 1 over lambda and figure out what those numbers are. So in particular, we're going to have to find some, we're going to have a function of lambda. If we start expanding it in 1 over lambda, we're going to start seeing zeta of 3, zeta of 5, and so on here. So what does supersymmetric localization do? Well, it gives exact results, but usually it doesn't give exact results for correlation functions of local operators. So using it to learn about local operators is not that obvious. So the idea of supersymmetric localization, let me explain very briefly why it doesn't tell us about correlation functions of local operators. So the idea is that there's a partition function, some theory that we want to consider, and we can deform this partition function, deform the action by some q exact term. I'm writing the anti-comparative q inside. So the idea is that if this term is q exact, then the partition function is independent of this t. Now, if the term that we added is positive definite, because the bosonic part is positive definite, then we can take a large t limit, and then z will be written as a simpler integral, where we're just, so it's going to be only the places in field space, the locus in field space where q psi is 0 that contribute. So this would be an integral such that q psi is 0. And we evaluate the action of those configurations, and there's a one with determinant, and that's exact. So ideally, after we do this procedure, this would be a finite dimensional integral. And we can insert, the whole argument goes through, if we insert q invariant observables, but unfortunately, these are not local operators because generically, q acting on some local operator is not 0 because if this were 0, then q squared would also be 0. But q squared is usually an isometry of the space, translation of rotations, plus some R symmetry transformation. And the isometry acting on local operators is, of course, not give us 0. So q squared would be some rotation plus something else, and the rotation part would rotate all. Would rotate the point x, it wouldn't leave all of x invariant. So supersymmetric localization is not good for local operators. What can we compute with it then? Well, the supersymmetric observables will be of two types, either integrated operators, where this problem doesn't happen, or there could be local operators inserted at special points where q squared is 0. The problem is, though, that q squared is 0 everywhere, then this integral is not going to localize to a matrix integral. So there's a tension between having observables that are local operators that we can compute and having a simple formula for the partition function after localization. Usually one or the other. Okay? So, what I'm going to do, we'll have two types. We'll have both types of supersymmetric observables. I'll relate S2 to these, and I relate SP to these. So we have S2, S2, SP, SP. We'll just integrate over two of the coordinates for the S2s, and then we'll put the SPs as special points where this happens. So that's the trick. So what is the setup? Well, we're in n equal 4 super angles. So let's just start with n equal 4 super angles on R4. That's the thing we want. It's a conformal theory, so we can put it on any other conformal flat space, and we just know how to put it supersymmetrically on the round 4 sphere. So let's just study it on a round 4 sphere. And there's an extra step, which is to deform it such that we insert these operators. So this deformation will deform while preserving a supercharge that belongs to an n equal 2 subalgebra of the n equal 4 superalgebra, and the supercharge will have the property that q squared will be 0 for some operators only 2 points on the 4 sphere. So this is the setup that best to consider. So in particular, so q squared will be 0 only at the north pole of the sphere and the south pole. The isometry part of q squared will be 0 only at the north pole of the sphere and the south pole of the sphere. Okay? So
you will be computing 4-point functions with the local operator north, south, and then integrating over the other two.
and 2 integrated, yeah. One north, one south, 2 integrated. So now let me explain what operators are. So because it's n equal 2, this is an n equal 2 subalgebra, let me say something about operators in n equal 2 superconformal field theories. Because it will be some of these. Well, let me try to see how much time I have.
5 minutes.
5 minutes? Okay. Yeah, okay, we can go with this. So, n equal 4 Supreme Mills is an n equal 4 superconformal field theory, but in particular it's an n equal 2 superconformal field theory with an SU2 flavor symmetry because it's the R symmetry. So for n equal to SCFT, the R symmetry is SU2 times U1, and within SU4, the R symmetry of n equal 4, there's an SU2 that commutes with this. And there's going to be two multiplets that are equally relevant. And n equals 2. And the first one is a conserved current multiplet. So a conserved current multiplet is going to have, among other things, a conserved current. And the, well, important operators for me will be the superconformal primary, which is a scalar, and then there's another scalar of higher dimension. So this scalar here has dimension 2, and it transforms into a three-dimensional representation of SU2, and it's a singlet under U1. This is a moment map operator. You can think of it as a scalar bilinear, and then the next scalar over here that I wrote as k has dimension 3, so this would be a fermion bilinear, and transforms. It's a singlet under SU2, which has some U1 charge. Okay, so these would be there's some multiplet from which I'll construct this deformation. And then there's other multiplet would be chiral or anti-chiral multiplets. And I'm not going to write down all the operators. The superconformal primary for the chiral operator multiplet is, I'll call it A sub P. We've got some other operators, and the anti-chiral one has, well, A, B bar, and other operators. And the point is that these operators have dimension G, and they're singlets under SU2 and have charges plus minus P under U1. And, well, this has charge plus P, and this has charge, this is delta equal P, and charge minus P. And on S4, we can have the following deformations. So the supersymmetric action that I'm going to be considering that preserves the supercharge is the following. Well, okay, so on S4, you can have deformations preserving Q. One of them will be using this multiplet, and the other one will be using those multiplets. The integrated operators will be using the top multiplet. The operators of north and south pole will be using the bottom multiplet. So using the top multiplet, it's a mass deformation, so it's conserved current multiplet. It can be coupled to a background vector multiplet. One can give expectation values to the scalars in the vector multiplet, and the scalars are coupled to J and K. So this is just adding mass. So it will look like this. The change in the action will be m times an integral over the sphere, ij plus k, and then some order m squared term. And the other supersymmetric insertions that we can have is A at the north pole or A bar at the south pole. These preserve the supercharge that doesn't consider. So I can tell you then how this is related to the operators in n equal 4 Supreme Mills that we've been considering.
So P is related to the SU2 model?
P is related to the U1R charge. So it's a singlet under SU2 and it has charge plus or minus P under U1.
And the stress tensor multiplet of n equals 4 splits into the conserved current plus P equals 2.
Yeah, so that's exactly what we're going to write down.
So AP is opposite of vector multiplet?
Correct. Trace of the scalar in the vector multiplet with RP. And AP bar would be trace by bar.
So and you do not consider Python?
they would enter in here, this J, not the.
But they figure out 3 J's, and I guess you take one there.
The three, yeah, okay, good. So this is just, yeah, so there's 3 J's, because they transform into 3 of SU2R,
Well, there's a function tree.
and here,
So there's a function tree.
that's right. But for now, let's just think about some n equal to superconformal fifth here with a U1 flavor symmetry, and then for n equal 4, we're going to have this an SU2 flavor symmetry. Yeah, so, but, okay, so there's going to be a total of 9 J's, and in this action, there's going to be 1 up here. But for now, this is just some component, of these operators. So K would be K plus K bar, because K is complex, and for J would be a certain component.
And you think J could be in the joint representation?
These are all in the adjoint of the flavor symmetry group. So for n equal 4 superior, the flavor symmetry, when viewed as n equal 2 superconformal, the flavor symmetry is an SU2 flavor symmetry in the adjoint. Okay, so maybe we can do the decomposition after the break. All right, we'll continue. I want to emphasize one thing, is that here the mass has dimension 1, K has dimension 3, so this, having this operator here is okay. This J has dimension 2, so this J wouldn't appear, and if we were to write down the mass information in flat space, on the sphere it can appear, and it's multiplied by 1 over the radius of the sphere. So this is something specific to the fact that there's a scalar bilinear in the mass deformation is something specific to the sphere. Of course, there's also an m squared multiplying the scalar bilinear. Okay, so just to remind you, there are 2 kinds of multiplets in n equal 2 superconformal field theories. One of them is a current multiplet that has these operators J and K, and the other one current multiplets or anti-current multiplets that have these operators A and A bar. And we can have a real mass deformation where we integrate ij plus k, or we can put A and A bar, A at the north pole, A bar at the south pole, and these deformations preserve the supercharge, the n equal 2 supercharge considered by S2. And now what's the relation between these operators and the operators in n equal 4 superaggregates that I was considering, S2 and SP? Well, S2 transforms in the 20 prime of SU4 R symmetry, and we can decompose that under the SU2, sorry, n equals 2 R symmetry, which is SU2 times U1, and then there's another SU2 that commutes to that inside SU4, so that would be a flavor symmetry from the point of view of n equal 2 theory. So this is the decomposition. So in the decomposition of this 20 prime, we see that, so here I wrote down in the parentheses the quantum, the dimensions of the representation under the 2 SU2s, and the index is the U1 R charge. So some components of this S2 are A2 and A2 bar, and then there's some other component over here, which is J. And as was emphasized before the break, for U1 flavor symmetry, there's 3 J's. If there's an SU2 flavor symmetry, there's 9 J's. So that's why this J transforms into 3 of this SU2 and in the adjoint of the flavor symmetry group as well. Okay? And if we were to do this decomposition for the chiral multiplets, this zero representation also decomposes, and the important part in that decomposition is that we get an A and an A bar from it. If you want a more conventional description of n equal 4 superaggregates, in terms of n equal 1 language, where we have chiral multiplets, so we can form these complex fields from the thighs, which I'll call Z, so Z1, Z2, Z3 are the bottom components of the chiral multiplets. And then under the n equal 2 decomposition, Z1 and Z2 form a hypermultiplet, and Z3 would be the scalar and the vector multiplet. Then this operator J that appears in the mass deformation is just trace of z1 squared plus z2 squared plus z1 bar squared plus z2 bar squared. And AP, which is the trace z3 to the p. And AP bar will be its complex conjugate. So trace z3 bar. Okay. So then, for what we should consider, this should be calculable using localization. So we should consider the n equal 4 super Yang-Mills action on S4. And then we should deform it by inserting all these operators. So we can insert AP at the North Pole with a coefficient tau p. We can insert AP bar at the South Pole with a coefficient tau p bar. And then we can have this real mass deformation j plus k integrated over the force field. Plus, of course, an order m squared term. These m squared terms are going to disappear in the end, so that's why I'm not writing them down. They should be kept track of. So, suppose that we could compute this using supersymmetric localization, and I'll explain how to compute it. Then, from that, what we can do is to take derivatives with respect to these parameters that we introduced and set the parameters to 0. So let's take the fourth derivative of log of the partition function, 2 derivatives with respect to the mass, 1 derivative with respect to tau p, and 1 derivative with respect to tau bar p. So that's just going to give this correlation function, so AP at the North Pole, AP bar at the South Pole, and 2 integrals over the sphere of Ij plus k.
Maybe going to explain why the 3-point function is there.
3-point function is there. There's another 3-point function contribution that comes from the order m squared term. That's there. Yes. That's there.
If you're going to write it out, you to say that it's 0.
No, it's not 0, but I'm not going to write it down. Okay, plus 3-point function.
Thank you.
So, I will tell you how to compute this thing. For now, let's assume we can compute it. From it, we extract this quantity, which is written in this n equal 2 language. This is the translation between the n equal 2 language and the n equal 4 language. So this will be related to the 4-point function. So when we have a bar, j, j, it will be related to the 4-point function of S2. Or the 4-point function SP, SP, S2, S2. But there's also this other piece where we have AP, AP bar, KK. And K was a dimension 3 operator. It's part of, you could also do the same computation and relate it to some operator in n equal 4. It's the operator that transforms into 10 plus 10 bar. So the fermion bilinear. Okay. So then you can write down this 4-point function as a linear combination of 2 things. Something involving SP, SP, S2, S2, and something involving SP, SP, and this other operator. That second 4-point function is related to the first by superconformal word identities. So I can use them, and I can re-express everything in terms of the 4-point function of SP, SP, S2, S2. So, after using superconformal word identities, we can write this, and I can write down the final formula. So there's some normalization constant that I'm write down because it's in the paper, times 2-dimensional integral. So let me write down the formula and then I'll explain. R to the 5th sine squared of theta 1 minus 2r squared ln r divided by r squared minus 1 squared t divided by u squared. And this is evaluated when, I can erase a little bit here. It's evaluated when u is 1 plus r squared minus 2r cosine theta, and v is r squared. So, let me first explain the equal sign, and then I'll explain this formula. So the equal sign uses, when you derive and you go from here to there, the first group theory to relate A, P, A, P bar, J, and K to operators in N4. The N4 language. The second thing that it uses is this word identity to relate the 4-point function AP, P bar, KK to the 4-point function of SP, SP, S2, S2.
For more than 4 points, this is genetically impossible because of these features.
For more than 4 points, this is genetic. This relation?
Yeah, I think it's order identity because that's the structures of space.
Okay. I haven't thought about that.
Sorry, what did you just say? The word identity? Or
You cannot use the word identities to relate to components like say
For more than 4 points. Okay, we're doing 4 points. Yes. Okay. Good. And the third one. So this 4-point function, AP, AP bar, KK, is given in terms of derivatives of the 4-point function SP, SP, S2, S2, because this is how the superconformal work. So you can also use, there are no derivatives here, so what I did, I integrated by parts. And now this is related to Balt's question about the 3-point function. Yes, this has the 3-point function, but after you integrate by parts, and add the 3-point function, you get this formula. So the final formula, there's no 3-point function contribution. So that 3-point function just goes away after the integration by parts. Okay? Now, so this is the equality sign. Now, this formula has 2 integrals over S4. That's 8 integrals, but I only wrote 2. That's just because using the rotational symmetry, so there's an SO4 rotational symmetry that's left over after we put one operator in the north pole, the other one in the south pole. That can be used to do 5 out of the 8 integrals, and then one can do another one that gives this. And then there's 2 more left in that. So this is the specific relation between the function t of u and v that appeared at the beginning of the thought and the quantity that one can compute using supersymmetric localization. So the idea would be write t. We know what t is in Mellin space up to a few undetermined constants, up to order 1 over lambda to the 5 halves. And then we just plug this in, do the integral, and set that equal to whatever we get from supersymmetric localization, and this is how we fix some of the constants that we have undetermined. Okay, good.
So I think you know this much better than you do. Isn't there there's some non-trivialization between operators on the sphere and operators on the
Sure.
flat space?
Yeah.
You have to worry about it there?
Hmm?
Do you have to worry about it?
Mm-hmm. Absolutely. So far what I wrote down is correct. I just didn't tell you how to evaluate this quantity. Okay. So let me say that now. So what is this partition function of so it's a function of m, tau p bar, and I guess the lambda and n. Okay, so let's just evaluate something slightly different first that's related precisely to this point. So let me introduce two other parameters, tau p prime and tau bar p prime. And this quantity is given by the following. So this can be done using supersymmetric localization. And so let me write down the formula and then I'll explain. The product I less than j, ai minus aj squared times h squared ai minus aj divided by h of ai minus aj plus m, h of ai minus aj minus m, e to the minus n over lambda, sum of ai squared. So this is the integral is over Cartan of SUN. So n integration variables with a constraint that they sum to 0. And these are the, so I goes from 1 to n. This is the formula for the S4 partition function of the n equal to star theory, so the math deformed n equal 4 theory that Pesman wrote down. So this would be the partition function when these parameters are set to 0.
Also, isn't any infinity?
Sorry?
Is it, what are those?
Yeah, sorry, times that some institute contribution. Okay. Yes. And the modification that allows us to compute the quantity over here is that we just introduce an extra factor, which is I tau p prime minus tau p prime bar times sum of ai to the p. Okay? So this is something one can compute, one can modify Pesman's result by this. The question is, how is this related to that? So, it was shown.
But you agree with the issue that the solution is a generating function in tau p prime and tau p prime, because the integral is not gonna, where a is large.
Sum over p?
No, I'm just complaining by the fact that,
Yeah.
well, okay, the assumption here doesn't matter. The fact
Some
that you can think about this thing only as a generating function in p prime.
Yeah, this is a generating function. The
But
question is,
we cannot, I mean, if you take t prime to be a number, tp to be 3,
yeah.
this is not, it's going to be divergent for any tp. I don't think it's going to converge. This is a simple, finite dimensional matrix integral. And the question is convergent or not.
But you have e to the minus n over lambda sum of a squared.
Yes, but it
goes back to the
it's
base.
going to be.
Let me think about it, because we actually did evaluate it. When p is even, I don't think there's a problem, unless I screwed up the sign. So this is some imaginary part, something.
Yes.
Times I, so I times I should be minus, and then when p is even, this should be okay.
I want both.
Well, I'm not going to do cube.
I is a to the p.
But it can still be evaluated when it's cubed. I think it can still be, well, I mean, it can still be evaluated in the saddle point approximation. The question is whether that makes sense or not. Anyway, I'm only, let's just, if it makes you happy, let's just do even p.
I was just asking you,
Yes.
if this is an actual function of just a formal expansion.
When p is even, then this is an actual function. Okay? And then, well, I wrote a paper about this with Zohar, Komargatsky, and Jaume Gomez, and a couple other people. And we explained that taking derivatives with respect to tau p prime and tau p prime bar is related to the insertion of these operators, AP and AP bar. But there's a subtlety because there's some extra mixing of operators that happens only on the sphere. So I can write down what happens if we take derivatives with respect to tau p prime and tau log p prime. Okay, so first, maybe I should mention that this h is the function that appears in Bessemer's paper. It's some, can be written in terms of some bars g functions. It's not that important. The instantons are going to depend on p, but I'm going to be ignoring them because at leading order in large n, the contribution from the instantons can be ignored. So I'm not going to worry about this in this talk. And now if we take derivatives of this partition function with respect to the mass, that corresponds to the assertion of this operator ij plus k. If we take derivative with respect to tau p prime, this corresponds to the assertion of AP at the North Pole. But because of this extra mixing, there's also an insertion that comes along with it of AP minus 2 at the North Pole, and then AP minus 4 at the North Pole, and so on. And same thing with tau p prime bar. This corresponds to AP bar at the South Pole plus some constant times AP minus 2 at the South Pole, AP minus 2 bar at the South Pole. So what these derivatives with respect to tau p prime and tau p prime bar do is they don't just insert what we want, AP at the North Pole and AP bar at the South Pole. They mix with, these operators mix with lower dimension operators. This is just because on the sphere, one can add some curvature coupling multiplied by the source for the operator. It wouldn't be present in that case. The fact that the dimensions differ by 2 because of this curvature coupling. So then, what do we do? This sounds like a tragedy that we don't get these operators. Well, we can find a relation between tau p prime and tau p. So to isolate AP at the North Pole and AP bar at the South Pole, we can compute the derivative with respect to tau p prime and tau bar q prime when n equals 0. So this would be the two-point function of these operators, and then diagonalize it using the Gram-Schmidt procedure, knowing that the only mixing that can occur is between these operators and operators of the lower dimension. So, first thing, compute this partition function as a function of tau p prime, tau q and its conjugate, and then equals 0. Compute this two-point function and diagonalize it, and then find the relation between tau p and tau p prime as the eigenvectors under these diagonalizations. Okay? So it's actually it gets quite complicated because of this Gram-Schmidt procedure. Well, also, this isn't a Hermitian matrix model anymore, so it's complicated, also complicated because of that. And so it's not just that it's not a Hermitian matrix model, it's also deformed by this mass. But somehow we still managed to compute those flat four derivatives.
So it's an expectation value, but it's an expectation value in a Gaussian matrix. If you take certain derivatives, it must be 0, and so on and so forth.
It's an expectation value in a Gaussian matrix model, but it's not a operator. So good luck with that too. So then
in practice, do you put P generic and compute it and then analytically?
I'll explain exactly what we do. So we do the following steps in practice. So first, for n equals 0, just to do the Gram-Schmidt procedure, we have the z is this integral product. Then these functions h go away. So it's just ai minus aj squared e to the minus n sum of potential as a function of ai. So this is a Gaussian matrix model with a potential. A large n, we ignore the instantons, and then we just solve it at leading ordering large n. Roughly, the idea is that a large n, these AIs become dense. So there's some eigenvalue density that I call rho 0 of x, normalized such that rho 0 integrated is equal to 1. And there are matrix model techniques that determine what this rho 0 is. In particular, rho 0 is for any polynomial potential, so this is a polynomial. Rho 0 is another polynomial that I'll call q over 2 pi times the square root of b squared minus x squared, where b is a number that needs to be determined. And q is a polynomial such that v prime divided by the square root b squared minus x squared. Oh, sorry, x squared minus b squared. Or minus q. This should go to 0 as x goes to infinity. So that's the condition that determines this polynomial. B is determined by the condition that integrates to 1. Okay, so I don't know how to do this in general. In practice, we just chose the pair of p and q and did this, and then took the two derivatives and then diagonalized this matrix. Okay, so then from that compute that matrix. So step 2, compute d log z, d tau p prime, d tau 2 prime bar, and diagonalize. So from that, we know what d by d tau p is in terms of d by d tau prime and correlators. So this is when n equals 0. Then the third step is to, so this one we cannot do, I don't know how to do it in practice in general, we just do it for a pair of tau p prime and tau p, for pairs of tau p and tau p. Then step 3, treat m as a perturbation. So that perturbation changes the, well, we can write down the formula. So then d log z by dm squared when m equals 0 is approximately m squared dx dy rho 0 of x rho 0 of y times some function of x minus y that comes from the two derivatives of this h with respect to this combination of h's with respect to m. So k prime, sorry, k is the same as minus h prime over h, where h is the product of our two functions that appears in the test paper. So this is how at fixed tau p prime and tau q prime, well, sorry, tau p prime and tau p prime bar, the log of z changes when we introduce m squared. So this is the second derivative with respect to m equals z. And this function obeys the equation k prime of x with some nice integral. It's a nice Fourier transform. So the omega 2 omega cosine of 2 omega x minus 1 divided by h squared omega. Okay, this may not look nice, but it's much nicer than products of large g functions. Okay. And now, after we do this, we evaluate this integral. Then after that, we take two more derivatives with respect to tau p and tau p bar, and then set everything set those taus to 0. So this is the last step. And I'll just tell you what the answer is. So there's a potential for very complicated formulas because there's lots of steps in the whole Graham-Schmidt procedure, perturbation theory, and so on. But surprisingly, the final answer is the two derivatives with respect to the mass, one with respect to tau p, one with respect to tau p bar of log z, and then tau p, normalized tau p bar log z. Can I just have another five minutes? Is okay? Or 3 minutes? Yeah, I'm just going to write it on the. Okay, so I'm just going to write it on the subject program. Okay. So this thing evaluated when n equals 0 and tau p is tau p bar equals 0. This has a very simple form. It's just an integral over omega times the Bessel function of square root of lambda omega over pi minus jp square root of lambda omega over pi squared divided by sinh squared over omega. So after all that Graham-Schmidt procedure and perturbation theory and so on, this is the final answer, just some integral over some difference of square root of Bessel functions. And then, this is the final. It depends on lambda in the arguments of the Bessel functions. And then you can try to extend this expression in 1 over lambda. And what you find is constant. And then you're going to have a 1 over lambda to the 3/2 term that multiplied by zeta of 3. And then the 1 over lambda to the 5/2 multiplied by zeta of 5. And then so on. That's some coefficient. So this is how this modified this four partition function knows about the zeta of 3s and zeta of 5s that appear in the string scaling amplitudes.
So what was the p-dependence?
There's some p-dependence. And the p-dependence is such that, well, okay, so I can just tell you, let me write down the formula for the Mellin amplitude. And that formula is such that when you take the flat space limit and you relate it to the string scattering amplitude, all the p's can go away. So, when you write down, so the final results after we use this constraint, I can just tell you what MP is at this order. So it's 1 over S minus 2, 2 minus P. Well, maybe I should be multiplied by n squared. 2 minus P, 2 minus P. So this is a supergravity piece. Then there's an R to the 4 contribution, which is P plus 1, 3. This is the Pochhammer symbol. 4 divided by 4, multiplied by zeta of 3, 1 over lambda to the 3/2. And then there's zeta of 5, divided by lambda to the 5/2. And then there's, so P plus 1, 5, S squared plus P squared plus C squared, plus some function of P and S, plus some other function of P. And so on. So maybe what I can do is to multiply this whole thing, so it's, I think, 2 over n squared in this equation. So then this has higher order directions. 1 over n squared. Okay, good. So then, we fixed, using also the result of Fernando and Yes and Eric, we fixed this for up to order 1 over lambda to the 5/2. So let me just make very brief comments. The order lambda to the 0 term here and order lambda to the 1 over lambda to the 3/2 can be derived either from the flat space limit or from this constraint that uses supersymmetric localization. So this is a precision test of the SCFT. This one is beyond supergravity. For p equal 2, I said this before, but this flat space limit and the supersymmetric localization result are enough to determine this completely up to order 1 over lambda to the 5/2. For p bigger than 2, one also needs this result for lambda and yesterday. Using this 4-point function, you can then extract CFT data up to this order. Because we know S2, S2, SP, SP, we can also extract, using methods developed by Fernando, order 1 over n to the 4th, on those dimensions. So there are, okay, so that's the story. There are generalizations in 3D that one can consider in APGM theory. And in that case, we're going to have a paper appearing early next week. We can actually check the R to the 4 contribution to the scattering amplitude. So we can derive it from supersymmetric localization using methods like this to all orders in G string. Well, to all orders in G string is just 2 orders that contribute. But we can show that the other ones are 0. And that's just because the S3 partition function for the mass-informed APGM theory, somehow it's better understood than the partition function of any course granules. This one has this instant time contribution that one would have to worry about. That one doesn't. So one can do more in 3D than in 4D. Okay, that's all. Sorry for that.
More questions?
So as you know, localization doesn't assume anything about planarity.
Sorry?
Localization doesn't assume anything about planarity.
Yes.
The best thing is if you can use similar things to see something that they don't think.
About?
Okay.
Yeah, I think so. I mean, one would just have to evaluate these partition functions to the next order in 1 over n squared.
Well, but I mean, here you are doing a trick that you are able to write a proper function using many space.
Yeah.
So you can change the integral in many space to the integral you expect before you give it out, and you can get something. But if you don't have a many space,
Yeah, okay, good. So there's several ingredients still, what I said. I mean, there's the localization part, and there's also the expression in Mellin space. Yes, we don't know the expression in Mellin space at the next order, I guess. Oh, sorry, maybe we do.
I think you have, for some cases.
For some cases, we do. So in those cases, maybe, yeah, this can be used. The tricky thing about this computation here is that one would have to worry about the instant time corrections in the next order. And that may not be so easy.
we don't say no, by non-planar I can say finite time, not one-word expansion.
Oh, finite n. About finite n, I don't know. I don't know what one can do, but I mean, certainly these are constraints on the 4-point function that must hold at all n, the ones derived from supersymmetric localization. Then if you have an ansatz for where the 4-point function is finite n, then you can plug it in. But more than that, I don't know. With the 1 over n expansion seems hard enough.
Further questions?